Let's look at two simple examples of triple integrals. Triple integrals are not much different from double integrals. In fact, the complexity is always about how to convert it into an iterated integral, then how to complete the evaluation. So for simple examples, we just wanted to illustrate this process over here. Okay. First of all, triple integrals are defined the same way as other definite integrals via the limit of a Riemann sum. And we're going to skip this part. Okay. And also we will talk about simple applications. So we actually use three elongated S signs, put them together, and V over here is the region we integrate a function with. Okay. So now the domain we are integrating the function with is a three-dimensional domain, a three-dimensional region. And when we do the iterated integral, we have now three choices. If we recall, in double integrals, we had two choices. We can integrate with respect to y first or with respect to x first. But now we have choice of integrating with respect to z first or x first or y first. It depends on which variable we integrate with respect to first, and we call these regions type 1, type 2, type 3. Really, it's just the same principle. Okay. So here is an example of how to convert a triple integral over a region described in the following way. You can see. So we fix x, y in the domain D. Okay. And for each fixed y, we see that z is changing between two functions, f of xy at the bottom and g of xy at the top. So if we look at what we have over here is this kind of domain. So this is D over here. This is D. And that's in the xy plane. Okay. And then we have over here a function above this D domain. And this function is going to be f. So this function over here is f xy. And then on the top, we have another one. This is going to be g of xy. And for each fixed xy, we have a small cylinder. It's a rectangular cylinder over here. The base is dx dy. And of course, this volume over here, this dv, is equal to the height, which is gxy minus f of xy, right? And multiplied by dx dy. So this one over here, this volume over here. Okay. But we are not finding the volume though. We are integrating a function. But fortunately, our example over here, we also have a simple function to deal with. Okay. So now what do we do? So let's start over here. Just first write down the triple integral. Okay. So we have the triple integral, and we have v over here. V is the region we're going to describe. And the integrand is z dv. Okay, so we use dv. dv simply means dx, dy, and dz. Okay, so dz over here is like that, dz. And the z is between these two. So now let's look at this domain V over here. V over here, we have this one. A lot of times we have to identify D by ourselves. So this we have over here, x, y, z. And we have x is bounded by three coordinate planes. X is equal to 0, y is equal to 0, z is equal to 0, and x plus y plus z is equal to 1. I'm bounded by this, bounded by these 4 planes. And we're going to try to find this D over here and find F, capital F, and capital G. So this is what we're going to do. So we're going to graph the region over here. We just need to have a rough sketch of the region. It doesn't have to be really accurate. See over here. Okay. So let's identify these 4 planes. We have 4 planes. 4 planes bound a region, a solid. X is equal to 0 is over here. This is x equal to 0 is zx, yz plane. Y is equal to 0 is over here. And z is equal to 0 is over here. So we have 3 planes over here, right? And then this is the crucial one. X plus y plus z is equal to 1. And we know how to do this. We look at the intercept, and then we have the triangle. It's just part of the plane. Okay. So this is the region over here. This is V. This is V. Now, we need to look at, say, how to describe it using something like this. Is it possible that x, y is fixed in D, and then z is between g of x, y and f of x, y? So we will try. Okay. And how do we do that? We really just say fix x, y, let z change. That means change up and down. So we try to see if we can find a domain so that the solid is bounded by a roof and a floor. And by looking at this one over here, we see this floor over here is z equal to the floor over here is z is equal to 0. Okay. And the roof, we can write down the roof over here is this one. Now, we don't know the function g of x, y yet, but we know the equation. So the equation is x plus y plus z is equal to 1. So that means z is equal to 1 minus x minus y. So in fact, we have the roof over here is 1 minus x minus y. So now we can describe this v over here. So v is really x, y in D. And what kind of D we have? We actually see this one over here. This is 1, and this is also 1. So this is our D. And for x, y in D, then we have z over here. It's going bottom to the top, and z is less than 1 minus x minus y, and bigger than 0. So that's what we have. Once we have this, then we have the conversion, converting this triple integral into a double integral. And inside the double integral, we have just a normal definite integral, but with x, y as parameters. So we have over here the double integral over D. And then we have over here inside from 0 to 1 minus x minus y. And the function z goes over here and dz. Okay. After we finish this, then we integrate with respect to dx dy. Okay, so that's the rule. And we have a simple integrand, so we can actually integrate this one over here. And you'll see we have just converted a triple integral into a double integral. So we still need to convert this double integral into an iterated integral, and then we can finish. But for the moment, this is going to be just 1/2 z squared, and plug in 1 minus x minus y and 0. And then we have dx dy, right? That's what we have. So let me actually divide this part into 2. Try to see if we can finish the computation over here. And then this is what we have, and d over here. This is 1/2 1 minus x minus y squared, and then we have dx dy. Now, let's look at which which variable we're going to integrate first, it doesn't really matter. Let's say fix x. If we fix x over here, then x must be somewhere between 0 and 1, right? And then once x is fixed, then y is going to be between 1 minus x and 0, because this is 0, and this one over here is 1 minus x, since the equation is simply over here. This equation over here is 1 minus x minus y is equal to 0, right? So now we can integrate this one from 0 to 1, okay? And then next one over here, we have from 0 to 1 minus x. And then 1/2 is a constant. You can take it down. Doesn't really matter. And 1 minus x minus y squared, and this is dy. After you finish, and then you do the dx. Okay. All right, so let's try very carefully. Okay, so now we integrate over here 1 minus x minus y squared dy. Now you may say, should we multiply that out? Let's not try to do that, because that will have many, many terms. But on the other hand, we can try to find this integrand without the antiderivative without much trouble. Just remember something like this. If you have something like a plus y squared dy, right? That's going to be exactly 1/3 a plus y cubed, right, plus c. So that's the same thing. So this one over here is simply 1 minus x minus y cubed 1/3, but you have a negative y. So this is going to be, you have a negative 1 over here, okay, and then plus c. If you take the derivative respect to y, you cover exactly the previous one. So now we put it back over here. We have 1/6, because 1/2 times 1/3 is 1/6, and we have negative, and then we have from 0 to 1, and this function over here we have 1 minus x minus y cubed, and plug in 1 minus x and 0, and then we dx, right? All right, so this is negative 1/6. Now we try to evaluate. This is from 0 to 1. If y is equal to 1 minus x, we get a 0. So we get a 0. And when we plug in 0, then we have 1 minus x cubed dx, right? So actually, we are pretty lucky. We have now positive. And from 0 to 1, 1 minus x cubed and dx. Again, we are facing this problem. Should we multiply it out? The answer is no, don't do that, and then we're going to have 4 terms. But on the other hand, we know 1 minus x cubed dx. What's going to be its antiderivative? It's going to be simply negative 1/4, 1 minus x to the 4th plus c, right? It can take the derivative and using chain rule to verify. So this one over here, now we have negative 1/24, right? And then from 0, oh, no more this one over here, because we already now evaluated, okay, integrated. So that's going to be 1 minus x to the power 4, and plus 1 and plus 0. And you can see it's pretty good. When x is 1, we get a 0. When x is 0, we get a 1. Negative becomes positive. So the answer is 1/24, right? So let's just briefly go over this process over here and try to see how we have solved this problem, and also try to identify where are the potential difficulties. Okay. First of all, this is number 1. We need to sketch the diagram. Okay. We need to sketch the diagram. We sketch the diagrams of 4 planes, and then we identify V. So this part is really crucial, and then we identify which variable to integrate first. And this is type 1. We can actually treat it as type 2 or type 3, but just for the sake of time, let's just do 1 over here. Okay, so we look at the diagram and we see that if we fix x, y in D, then z is changing between 2 functions. One is 0, the other one, we usually say the floor or the roof, and that's going to be fine. The floor function and the roof function, right? And then between these 2. And this second step over here is crucial because now it enables us to convert a triple integral into a double integral. Inside is just a definite integral, a single integral, you can say. And then evaluate it very carefully. And here we learned that not to multiply things out unless it's necessary, because otherwise we will have tremendous amount of work to do. But on the other hand, for examples like this, try to see if we have a simple way to evaluate to find the antiderivative. And we plug in things carefully, and then we get an answer. I'm pretty confident this answer over here is correct. All right, that's it for example 1.